Okay, thank you everybody for staying until the very last talk of the workshop. This is joint work with George Birbas, Aris and Alexandros. And I have to give credit for the slides to my co-authors, mostly Alex. So this is a recent work. This was presented in AAAI this year. So, I mean, not surprisingly, this is about distortion, but and you know, after 9 great talks on the subject, any motivational example is kind of redundant, but let me give a very short one. So let's say we want to ask people to vote about the winner of a hypothetical battle between Superman and Batman. And well, this is like the typical problematic case where roughly half the voters slightly prefer one of the candidates, while everybody else strongly prefers the other. Right? And of course, well, here you cannot do much more than decide by majority. And these examples showcase that, you know, if we actually knew how the participants value the 2 different alternatives, maybe we would have decided differently. Right? So the idea is that, well, if we only have ordinal information, then our decision making doesn't reflect the opinions of everybody. And well, the main question is, well, how bad can this be, right? How far can we be from the decision that we would take if we knew the complete cardinal information that lies behind like the ordinal info that we get? So let me introduce my basic notation. We have n agents, m alternatives, and we assume that each agent has a value for every alternative. However, they don't report these values. What they report is a preference ranking over all alternatives. So each agent provides a ranking that is consistent with their actual values, but we don't immediately have access to them. And an ordinal mechanism or a voting rule takes all these preference rankings and, well, it aggregates them to a single winning alternative. By the way, here I'm going to focus entirely on single winning elections and on deterministic mechanisms. So what is the objective? Well, we want to select the alternative that maximizes the sum of the values of the voters, right? So namely the social welfare, and of course the social welfare is defined with respect to the cardinal profile that we don't immediately see. And for the 10th time in the last 3 days, let me define what distortion is. So the distortion of a mechanism is the worst case ratio between the maximum possible social welfare that we could achieve by any alternative over the social welfare that the mechanism achieves, the social welfare of the alternative output by the mechanism. And this was introduced almost 15 years ago by Procaccia and Rosenheim, and it follows the same rationale with the approximation ratio or price of anarchy, all these worst case notions. And of course, we can define it for other objectives as well. I mean, we've seen this with social cost in the metric setting, but one can use slightly other. I mean, we just had like this discussion about the NAS welfare, for instance. Okay. So what do we already know? Well, these have been mentioned at some point, maybe multiple times, but let's state them and have them as a point of reference. So when we stick to deterministic mechanisms, we know that we can achieve distortion of order m squared. And well, we know that this is the best that one could hope for, unless we allow randomization. Once we allow randomization, this theta of m squared becomes roughly square root of m, right? And although we're not going into randomized mechanisms at all, it's good to have like this to compare with, because what we do instead is we get some extra information. I have to mention here that all these results assume unit sum valuation functions, which is kind of the standard in this setting. However, for many of our results, actually for most of our results, we don't need any assumption, any normalization assumption on the valuation functions. And it will become clear. But in any case, I mean, you can think of unisum valuation functions throughout the talk. So let's visualize a little bit what the different settings can be here. So, well, on one extreme, we have the full information setting where we know the cardinal valuations. And of course, there, the distortion is 1, because, I mean, we can check each candidate. The standard setting, the setting where most work has been done in distortion, is when we have full access on the ordinal preferences of the agents. There are several recent very nice works on the setting where we have limited ordinal information. So we don't even have access to the full ordinal profiles, right? So we can still do something here, although we have like very limited information, but our work lies here, right? So between ordinal info and cardinal info, so we assume that we know the ordinal preferences, and we try to improve the distortion by accessing limited cardinal information, right? And this is a relatively new line of work. So let's see exactly what this means, right? So the agents can still rank the alternatives like in the standard setting, but here we hope that we can actually elicit some extra cardinal information by asking simple queries. And by simple queries, I mean 2 different types of queries. The most straightforward thing to ask is value queries, where we ask for an agent and an alternative, and then the oracle gives us the value that this agent has for this alternative. And well, I'm going to mention it here and not repeat it again in any of the results, but given that all of our results are asymptotic, it doesn't really make a difference if we have like a noisy oracle, or as long as we have a constant approximation of the values, everything works. Now, the other type of query we study is comparison queries. At some point today, I think Kamesh talked about comparison queries. This is a slightly different type of, so we don't compare directly agents with each other. So here the idea is we ask agent I whether the value she has for alternative X is at least D times more than the value she has for alternative Y. So if this is true, the answer is yes, and it's no otherwise. So, well, why comparison queries? Because this is a type of query that is not extensively studied, but essentially what happens is it's easy to see that these are a weaker type of query, right? In the following sense. So for any comparison query, it suffices to ask 2 value queries. If we know VIX and VIY, then we can directly answer the query. Now, if we wanted to simulate a value query using only comparison queries on the other hand, and we have no normalization on the valuation functions, this is just impossible, right? So, and even if we have like we assume unit sum valuations, still to simulate one value query, we need like log or log square comparison queries. So in a specific sense, these are weaker than value queries. But the main motivation behind them is that the cognitive complexity of a comparison query is not much higher than that of a direct comparison. And in fact, this goes back to the original utility framework of von Neumann and Morgenstern, where the idea of having cardinal utilities is based on the fact that the agents not only can they compare alternatives with each other, but also lotteries over alternatives. So for instance, agent I should be able to tell whether she prefers alternative I with certainty or alternative B with probability 1/2. And if we assume risk neutrality, this is equivalent to asking I whether she values A at least 0.5 times as much as B. So, but in general, I mean, except for a very specific part, I'm going to talk about value queries. So I'll come back to comparison queries, but in a while. So let's see how our voting mechanisms look like. So we can, let's say, we can decompose our mechanisms into two kind of independent parts. So the first part is a query algorithm that takes as input the ordinal preferences and decides who to ask and for whom, and gets back a bunch of answers to a bunch of queries. And then we have a modified voting rule. I say modified because a typical voting rule would just take the ordinal preferences, but here, of course, we want to take both the ordinal preferences and the extra cardinal information we extracted. And then we decide the winner. So let me say here, while we only consider deterministic mechanisms, here we could have randomization in either part. Okay, so the idea is to go from this area where we have only ordinal preferences and we have distortion squared of m, or so m squared or squared of m for randomized mechanisms, towards here where we have distortion 1. And of course, well, a trivial thing to do is ask everybody m queries and then we get distortion 1, but of course, the goal is to improve the distortion using only a limited number of queries per agent. So let's see what's the most straightforward thing to do, right? So let's say somebody said, look, you have lambda queries per agent. Do whatever you want with that. Of course, I could be like adaptive. I could do something clever. But let's say I'm lazy. I want to do like the most dumb thing here. So what I can do is just ask each agent their top lambda alternatives, right? So for the first lambda positions, I have like access to the full cardinal values. And then this already reveals some of the hidden welfare, right? So let's decide just on that, right? So then we maximize this revealed social welfare and pretend that everything that we didn't ask has value 0, right? So we pick the alternative that maximizes this revealed social welfare. And well, naive as it is, this already gives us some improvement. So the distortion of these voting mechanisms that we call lambda PRV is order of m over lambda, and it works for any class of valuation functions without normalization. So this means that just by asking one query, we get an improvement from m squared to m. And we can get distortion of square root of m by asking square root of m queries. But then again, if we want to go to constant distortion, well, we still have to ask, well, not all of the alternatives, but a constant fraction of them at least. So somehow this gives an improvement, but the more we ask, we don't get as much as we probably would expect. And there's a simple explanation for that. I mean, a simple intuition for that. So let's see what happens, right? So for the first lambda positions, we have full information. However, the way I describe the mechanism, what it does is that it throws away all the ordinal information we have, right? So it kind of, so if I ask like in the first 5 positions and I have ordinal information for 100 more, I just ignore this information, right? So clearly this is kind of a very wasteful way to decide. So let's do something a little bit more clever. So again, we're going to ask for the top alternative. So let's fix an agent, I. So we ask about what's the value of the top alternative, and let's say it's VI star. Now, instead of asking on the second position, third position, and so on and so forth, we define K threshold values, alpha 1 through alpha K. And now the idea is we want to pinpoint the position where the value of an alternative becomes VI star over alpha 1. So I want to find this position. So this is, according to I's ordering, this is position 1. I want to find the position where the value of I has dropped to this, or roughly to this. And well, of course, I cannot do that with a single value query, right? But I can do a binary search, right? So I can ask like in the middle of the profile, because the profile is ordered, right? So I can ask in the middle, and depending on whether the value is larger or smaller than that, go left or right and repeat until I find exactly the point. So in log M queries, I can find where at which position the value has dropped to VI star over the first threshold. And of course, the first threshold doesn't have anything special. I can repeat the same thing for the second threshold, and so on and so forth. So this means I have identified a few points here. I have spent roughly K log M queries. And well, this gives me an estimate of the whole valuation function, right? I mean, this is not continuous anyways, but for the sake of explaining the idea, let's say that these are so many that I almost look at a continuous line here, right? So by doing what we did here, we get a stepwise approximation of the actual valuation function. So let's call this the simulated valuation function, and denoted by a tilde. Now, this is, of course, a lower bound on the actual thing. And we use this to maximize the social welfare, which is not the actual social welfare, but it's like, let's say, the simulated social welfare, right? That assigns, for instance, to someone in this position, this much value instead of the actual thing, which is something somewhere here. Okay, so we set the thresholds carefully, and in this case are powers of m, in fact, well, roots of m. So it's, we start with 1 over k plus 1, 2 over k plus 1, up to k over k plus 1. And well, we calculate this step function, and then we use these step functions along the different agents to find the alternative that maximizes this simulated social welfare. And it turns out that by using K log M value queries, we can achieve distortion that is M to the 1 over K plus 1. And still, we don't need any normalization. And well, these two direct corollaries of that is that we can achieve distortion squared of M, which beats the best known randomized mechanism by using logarithmically many queries per agent. And if we go to log squared queries per agent, we can achieve constant distortion. Now, there's also another cool thing about that. Well, the main observation here is that if we know somehow VI star, and this is the part that I'm coming back to comparison queries, if we know VI star, then we can compute the simulated evaluation functions only by comparison queries. So let's go back, right? So in order to perform the binary search, once I know VI star, well, I only need to compare the value at any position with this quantity, right? So once I know VI star, I don't need any more value queries. So I could do this thing with one value query and like k log m comparison queries. But essentially, the main question is, can I actually find VI star or approximate it only with comparison queries? Well, in the beginning, I said that if I want to simulate a value query only with comparison queries, this is impossible. And so here we assume that we have unit sum valuation functions. And if we have unit sum valuation functions and we have enough thresholds, so here enough thresholds means like logarithmically many, the points are dense enough so that everything falls within a factor of 1 plus epsilon of a neighboring point that we have already calculated. And now, because everything is expressed in terms of VI star, and we know that everything sums up to 1, essentially we have a quantity that VI star is a common factor, and then we can estimate VI star within a multiplicative 1 plus epsilon factor. So assuming unit sum valuations and using log n binary searches, therefore log squared comparison queries, we can estimate VI star by some quantity UI. And then use this in order to find the simulated valuation functions and extract like I mean, essentially do the same thing like before and elect the winner of the simulated social welfare. Now, because we could achieve like constant distortion with log squared value queries, and we don't spend more than this for estimating the VI star, this means that just using comparison queries and without spending more than log squared queries, we can still achieve constant distortion. Okay, so what about lower bounds? Well, we saw in the very, very first stupid mechanism that we can achieve just with one query, we can achieve like distortion of order m. And of course, this is tight as long as we have unrestricted values. For unit sum valuation functions, the lower bound is weaker and we don't have a better upper bound. So, but we do have a conjecture that I will state in a couple of slides. So these are lower bounds for a single query. So once we go to many queries, we have a more general but a slightly weaker lower bound. So for any constant lambda, the distortion is at least m to this quantity. For instance, for 2 queries, the distortion is at least m to the 1/6. But what is really nice here is that, well, as long as we are below a logarithmic number of queries, we cannot achieve constant distortion. So in order to have constant distortion, we really need log m or almost log m value queries. Okay, so I mean, the picture is something like that, right? With the upper and the lower bounds. And so the conjectures that I'm going to state now are about, well, they're about the unit sum, the one query for unit sum valuations that doesn't show in the picture, and for this area here. So let me close with those. So the one query conjecture states that, well, when we have unit sum valuation functions, even with one value query, we can achieve square root distortion, square root of m distortion. And the log m queries conjecture states that even for unrestricted values, we can achieve constant distortion just with a logarithmic number of value queries. So, I mean, if you ask me which one I believe stronger, I would say the second one. I mean, I would be very surprised if we really need more than log m queries for achieving constant distortion. But you know, I think both are excellent problems, definitely non-trivial. And of course, there are several other directions that we haven't explored at all in this work, like what happens if we allow randomization, either for upper or lower bounds, or if we study multi-winner elections instead of single winner. What happens in related settings like participatory budgeting, or what if we study this trade-off in metric spaces. And there was a related paper of Ben Elliott and Wenan in last Wine, I think, about this. So I will stop here, and I'll be happy to take questions.